to actually do a spring problem, you need a spring, and you need a weight on the end of it, and you have to take a few measurements. So the key measurement is kind of surprising. It's Hooke's law. The force is equal to the springiness constant times the change in position. So we're going to do this in American, because this little weight that I have right here is 8 ounces of brass, which is a half a pound. So that's a force. So I can put a 0.5 right here. And I have to do the following. And this actually decides everything. It's really funny. You take this spring and you mark its position, with your little ruler, and then you let the weight come down in your gravitational field, and you measure how far. How far did that weight displace the end of the spring? And then you mark that down and you do Hooke's law. So in my case, it was half a pound. The displacement was 5 inches, 5 out of 12. You want to measure that very carefully, because this K, this 1.2, goes right there. The mass goes right there. In our case, we'll be doing foot-pounds. So we get an equation that says 0.5 y prime plus 1.2 y equals 0. So, or y double prime, 0.5 times y double prime. So it's a force. It's a composition of forces. Multiply it through by 2, and I get y double prime plus, instead of 1.2, this is now 2.4, y equals 0. So there's our setup, and you recognize one of these. You recognize what happens with that. We're going to get the r is equal to the square root of the negative of that, which comes out to be 1.55i. And that gives us, for our solution, we're almost done, y equals c1 cosine of 1.55t plus c2 sine 1.55t. Just the springiness personality, the mass and the springiness personality decided that 1.55, which is everything. So now let's take a look at the experiment. What you do is you pull this thing down, let's just say, and you mark down how far you pull it. Let's say you pull it down 3 inches, and then you let it go. And you can see the spring goes up and down, and the 3 inches that you pulled it down is what's going to be the amplitude. That's what's going to happen. 3 inches is going to tell us how much this thing displaces as it goes back and forth. So if you did that, you'd have, for initial conditions, you'd have, okay, y of 0 equals 3/12, otherwise known as 0.25 feet. Got to have it in feet. Everything's in feet. And then y prime of 0, did you notice that I pulled it down and then simply let it go? So I did not apply any initial velocity. So the initial velocity was 0. Then the personality of the spring took over. So using those two pieces of information, you can see, put in the 0. The cosine of 0 is 1. Sine of 0 is 0. So I get the 0.25 right here. The 0.25 happens there. And then y prime of 0, well, this term becomes a sine. Sine of 0 is 0. Here's where cosine lives, and I end up with a 1.55 C2 equals 0, which forces C2 to be 0. So that's ball game. We got everything. This is the equation. And I always feel like it's such a ripoff, because you know what the equation says? It says the spring goes up and down. Whoa! And is the initial condition 0.25? Yes, it is. Wow, that's amazing. And it goes up and down. But what is slightly amazing is that if you take your measurements very carefully, you'll get a halfway decent timer. This is the heart of the problem. How fast? Remember time. Time is the horizontal axis here. You should have something that models the position of the spring pretty well as time goes by. Now, if we kept this video going, what you'd see happens is there's two things happening that's kind of bad. One is the spring isn't staying the same amplitude. It's the amplitude's decreasing because there's damping. We're in an atmosphere. The spring has to fight its way up and down. And there's a little friction just because of the spring. Then the other thing is, I don't know if you can see it from here. I think you can see it. Do you notice how the spring is not riding directly straight up and down? Because I was a slob when I pulled the thing down and let it go. I didn't make it perfectly vertical. So we're losing some energy in a side-to-side motion here. So the spring is dying out. So if we actually took measurements, like, you take your ruler and you stick it over here, and you have a watch, and you mark the timing with the watch, and you take your readings just from still pictures, it wouldn't be dead on. We were just too sloppy. But if you're really careful, if you're really careful and get accurate measurements and make sure the spring is just going straight up and straight down, you get pretty good results for the first minute. For the first minute that's bouncing around. But I always feel like, you got all this work, and what does it tell you? Well, it tells you the spring goes up and down. Amazing. All right, there you go. That's how you do one of these in real life.